Welcome back. I don't know how many of you have had an MRI before. MRI stands for magnetic resonance imaging. It's a non-invasive spectroscopic technique using radio waves to spin flip odd number of nuclei under a strong magnetic field. The person lies on a bed that moves into the MRI machine, surrounded by a strong magnet. And the images obtained can be interpreted by a doctor or a medical professional for diagnosis of certain conditions. Okay, in this lesson, we're looking at low-resolution 13-carbon nuclear magnetic resonance spectroscopy. So the study dot point, we're looking at structural determination of organic compounds using low-resolution carbon-13 nuclear magnetic resonance NMR or spectroscopy. Okay, we've come across the electromagnetic spectrum before. This time in NMR, we're looking at the radio wave length of the electromagnetic spectrum, especially around 10 to the power 8 hertz. The radio wave section has a longer wavelength than both visible light and infrared light, which we've seen before. Okay, so let's look at some principles of NMR to begin with. If we have an odd numbered nucleus, then it's going to act as a mini magnet. And for an example, let's look at a 13-carbon nucleus. It's got 6 protons, and if it was 13 carbon, it would have 7 neutrons, giving a total of 13 particles in the nucleus or nucleons. If you have an odd-numbered nucleus, then it can act as a mini magnet. So in the presence of a magnetic field, the nuclei that have got odd-numbered nucleons, behave as these mini magnets, and in the presence of a strong magnetic field, odd-numbered nuclei absorb radio waves and spin flip. And then when the nuclei flip from high to low energy, energy is released and recorded on an NMR spectrum. So 13-carbon NMR spectroscopy is an analytical technique using radio waves and magnetic fields to provide information about the number of non-equivalent carbon environments in an organic compound. And we're going to talk more about that in the next few slides. Okay, so let's look at some of the principles of low-resolution 13-carbon NMR. So it's all calibrated against a molecule called TMS, which is tetramethylsilane. And that is our calibration point. So the x-axis is chemical shift, measured in ppm, but we read the spectrum from the right, so starting at 0, reading from right to left, which is a bit unusual. The number of peaks, excluding TMS, and we've got here 1, 2, 3 peaks, indicates the number of different carbon environments, non-equivalent carbon environments in the organic molecule. And that's the first bit of information that we want to look at. Sometimes the peak is shown for TMS, other times it's not. So don't count the peak at 0 part per million. The chemical shift, which is the x-axis, is the resonant frequency of an atomic nucleus relative to a standard, and we can compare these with values in the data book. Now, if we have some symmetry in the molecule, so identical parts facing each other around an axis, then that will affect the number of non-equivalent carbon environments that we have in the molecule. And again, we'll explain that more later in this lesson. Okay, so the key takeaway is the number of peaks, excluding TMS, which is our calibration point, equals the number of non-equivalent carbon environments. So we count the peaks excluding TMS, 1, 2, 3, 4, 5. And then if we have a look at the compound that's made this spectrum, we actually have 1, 2, 3, 4, 5. We've got 6 carbons, but we have 5 unique carbon environments. Just looking at the carbons, so the circular carbons are in the same environment. The square carbon is in a unique environment. Then I can draw a diamond for carbon 3. I can draw a star for carbon 4, and I'll make a double circle for carbon 5. So that's showing 5 different carbon environments. Then what we need to do is use the chemical shifts to identify the type of carbon environment by matching that to the data book. So the first thing to do is look for any symmetry within a molecule. And we mentioned that the methyls here are in the same chemical environment. If we compare that to tetramethylsilane, TMS, that is our calibration molecule, it has a silicon where you would normally see carbon in a tetrahedral shape. Each of these methyl groups is in the same chemical position, chemical environment as each other. So all of these carbons are in the same environment. So there's one carbon environment due to symmetry amongst the molecule. If you think about it, it's a tetrahedral shape with 4 equal methyl groups, equally symmetrical methyl groups coming off the silicon. So there's one carbon environment. Okay, so now if we analyse an actual 13-carbon NMR spectrum, we know that we don't worry about the TMS peak, so we ignore that because it's just a calibration point. But then we can look at the location of the various peaks that are shown, and we can compare the location of those peaks with information in the VCA data book. You're not expected to remember any of this information. You'll always be provided with it, either in the stem of the question or in the data book. Now, unlike in IR, the peaks in NMR generally are very narrow. They don't span the entire chemical shift range shown in the data book. Also, the chemical shift ranges can vary somewhat depending if there's a presence of an electronegative atom in the molecule. So presence of fluorine, oxygen, nitrogen and other halogens or Fonkel shows the presence of an electronegative atom. Halogens are shown by X. So X can represent fluorine, chlorine, bromine or iodine, which are all electronegative. So we want then to match the peaks with the data in the data book. Okay, as I just said, the presence of any of the Fonkel atoms often causes the chemical shift to move downfield. Now, downfield we mean towards the right. If we shift a chemical shift downfield, it means we move more to the left. So the presence of Fonkel or halogens will actually shift the chemical shift further downfield. Upfield means closest to TMS, which is our calibration point. Okay, let's have a look at a worked example. An organic compound contains nitrogen, so we're told that. Complete the following table using the 13-carbon NMR spectrum, which is shown on the slide. So we have a chemical shift at 20 part per million, and we have another one at 50.2. So if we look up 20 part per million in the data book, we can see that it corresponds to a carbon that is part of a methyl group attached to the rest of the molecule, or it's a carbon part of a CH2 that's connected to 2 R groups. So either of those for 20 part per million. At the 50.2 part per million, it's a carbon that's attached to an NH2 group and the rest of a molecule, or a carbon attached to an N with the rest of the molecule. So either of those options is correct. So 1 mark for identifying either of those unique chemical environments. Okay, so let's summarise what we've learned. The number of peaks excluding TMS, which is the calibration point, indicates the number of unique carbon environments in the molecule. So always look for some points of symmetry within the molecule. Read the spectrum from the right to the left. So the right is upfield, the left is downfield, and assign chemical shifts based on the values in the data book. The presence of electronegative atoms such as fluorine, oxygen and nitrogen moves the chemical shift values downfield. So in the example 2-methylpentane, this is the calibration point we have 1, 2, 3, 4, 5 peaks, indicating 5 non-equivalent carbon environments, which are shown in the molecule here. So carbons 1, both in the same chemical environment, methyl groups connected to carbon 2. Don't forget Funkel, the order of decreasing electronegativity, which we've come across before. Order fluorine is the most electronegative element, followed by oxygen, followed by nitrogen, followed by chlorine and the other halogens. What's coming up next is low and high resolution proton nuclear magnetic resonance spectroscopy. See you then.